And we also need to monitor sound. I'm not sure. One sec. Let's check that we are using the correct microphone. Are we using the correct microphone? Yes, we're sharing the correct screen. I'm thinking about biomedical imaging. Why is this in biomedical imaging? Well, magnets are kind of related. Let's actually talk to. Let's talk to one of the models. Hey, let's talk to Perplexity for a sec. Sure, can change the voice now. Okay, can you tell me how magnets are relevant to biomedical imaging?
Sure, magnets play a crucial role in biomedical imaging, particularly in magnetic resonance imaging, or MRI. MRI uses strong magnetic fields to generate detailed images of the inside of the body.
Okay, how about TMS?
Transcranial magnetic stimulation, or TMS, is a non-invasive procedure that uses magnetic fields to stimulate nerve cells in the brain. It's often used to treat depression, especially in patients who haven't responded well to other treatments. During TMS, a magnetic coil placed on the scalp generates magnetic pulses that pass through the skull and stimulate specific brain regions involved in mood regulation. TMS is considered safe and has been shown to be effective for many people with treatment-resistant depression.
Yeah, how is it relevant to magnets again?
TMS is relevant to magnets because it uses magnetic fields to induce electrical currents in specific areas of the brain. The magnetic pulses generated by the TMS device can penetrate the skull and influence neural activity, which is how it affects brain function and helps treat conditions like depression.
Can you do much shorter responses? How is, again, just in one sentence, how are magnets relevant to biomedical imaging?
Magnets are used in biomedical imaging, such as MRI, to create detailed images of the body's internal structures by using strong magnetic fields and radio waves.
Okay, how is a simple magnet is relevant to MRI?
A simple magnet is not powerful enough for MRI. MRI machines require strong, precisely controlled magnetic fields to produce detailed images.
So those will be electromagnets, are they?
Yes, MRI machines use powerful electromagnets to create the strong and stable magnetic fields needed for imaging. These electromagnets are essential for producing clear and detailed images of the body's internal structures.
Okay, how can I simulate an MRI machine, say, with four rectangular magnets?
Simulating an MRI machine using a rectangular magnet would be challenging because MRI requires a very uniform and strong magnetic field, which is typically achieved by highly specialized superconducting magnets. If you're looking for a basic magnetic field experiment, you might consider using a small permanent magnet. However, keep in mind that it won't replicate the complex and precise environment of an actual MRI system.
I guess again, how, just in simple terms, how do I simulate an MRI machine using simple basic magnets?
To simulate an MRI with a simple magnet, you can create a basic setup by using a small, strong magnet to demonstrate magnetic field effects. For a very basic experiment, you could show how the magnet affects small metal objects, or compare how magnetic fields interact with different materials. However, keep in mind that this won't replicate the detailed imaging properties of an actual MRI machine. The key aspect of an MRI is the uniform magnetic field and radio frequency pulses used to create detailed internal images.
Okay, so how would you simulate the basic workings of an MRI machine?
To simulate the basic workings of an MRI machine, you could demonstrate the concept of magnetic resonance. For a simple activity, you could use a handheld MRI model or educational kit that explains how hydrogen atoms in the body respond to magnetic fields and radio waves. You might show how these atoms align with the magnetic field and how radio frequency pulses cause them to emit signals that can be measured to create images. This would help illustrate the fundamental principles behind how MRI imaging works.
Okay, what would you see on the screen?
On the screen, I would display a simple animation or diagram showing how hydrogen atoms in the body align with the magnetic field. Then, I'd show how radio frequency pulses are applied, causing the atoms to emit signals. Finally, I'd illustrate how these signals are collected and processed to create an image, highlighting the concept of magnetic resonance. This would help viewers understand the key steps involved in MRI imaging.
Sorry, say again. What exactly would be visible on the screen?
On the screen, I show an animation illustrating 3 main steps. First, how hydrogen atoms align with the strong magnetic field. Second, how radio frequency pulses temporarily disturb the alignment. And third, how the signals emitted by the hydrogen atoms are collected and processed to form an image. This would help visualize the basic principles behind MRI imaging.
Wait a sec. So what if we wanted to do like a single page web application, interactive web application?
For a single-page interactive web application, you could create a user-friendly interface that guides users through the MRI process. You could include 1. Visuals and animations showing how hydrogen atoms align with the magnetic field and respond to radio frequency pulses. 2. Interactive controls, allowing users to adjust the magnetic field strength or radio frequency parameters and see the effects on the simulation. 3. Explanatory text and pop-ups, providing insights into each step, helping users understand the underlying principles. This would make the MRI concept accessible and engaging for users.
Okay, I would actually need to see it. Can you provide a basic prompt? So we have an experienced JavaScript developer. Hey, I want to do it as a single page web application, interactive. How would you ask a senior developer to do it?
To ask a senior developer to create a basic interactive, single-page web application to simulate MRI principles, you could say, could you develop a single-page, interactive web application that educates users about MRI principles? The app should visually demonstrate how hydrogen atoms align with the magnetic field, respond to radio frequency pulses, and emit signals that create an image. It should include interactive elements where users can adjust parameters and see real-time changes. Please ensure the interface is user-friendly and educational.
Yeah, let's actually try it out. Where is the chat? Right. And we have some other another long prompt that we normally use. Question is, which model? Let's go for Gemini 2.5 Pro for a sec. We have this another prompt. Where is it? Let's have a gazillion of prompts. Yes, single page, interactive. So we're just using HTML, JavaScript, CSS in a single file at the moment to start with. So we're not using React, TypeScript, Tailwind, CSS, Google APIs. Wanted to work with keyboard, mouse, and touch, educational, interactive, and accurate. Yeah, we would like sonification if possible. And we'll have a play demo. We will have a play demo. And let's see what it can do. I'm not sure which other models are good at coding. So which model? Yeah, we do have a so. Okay, let's see. Let's read that. Okay, so we're building an interactive web app to teach MRI principle. Applies the single HTML file. Yeah, interactive. Animated hydrogen atom aligning and processing. Hey, can we just give it back to... Oh, you can't actually do it. Can't give it to... Yeah, the voice models. Kind of hopeless because you can't give them text. Okay, but we have a code. We have a code. We already have a MRI simulator from before. Yeah, it's not very great. So hopefully we can do better than this. So now what? Applying main field, apply RF pulse, apply gradient. It was some detecting signal. Yeah. I assume that's the sample within the MRI machine. With the MRI machine. Oh yeah. So we'll have a second version of it. Index HTML. Okay, we have 700 lines of code. Some Gemini always making the same. That's not an error, it's just I'm worrying about the WebKit appearance. This we can fix it later. Code will still work. Okay, so we have what hopefully is Mueller. Okay, flip doesn't do anything, does it? Is the demo working? Turning on main magnetic field, applying 90 degrees RF pulse. It's not working, is it? The demo is not working. The demo. Let's have another. Another bot. I'm going to stream. Can you explain what do you currently see on the screen? Just briefly and make it fun.
Alrighty, picture this. On the left, it's like a tiny proton party with all these arrows doing a little dance. And on the right, you've got this wiggly red signal, like the record player for their proton party music. It's like a little MRI simulator having a blast.
Okay, so it is an MRI simulator. Are we meant to be able to see the output image or something of the sample? No.
That's a great question. Usually an MRI simulator would show you the final image, but this one seems to be focusing on the basic principles, like the behavior of the protons and the signal they produce. It's more about learning how things work behind the scenes rather than showing the final picture.
Okay, I don't think it's working great. Can you tell me what is happening? What B0 is on, B0 on? What? Ready, press B0 on to begin. Aligning protons with BO field. Okay. RF pulse. Yeah, it doesn't do much, does it?
It looks like the B0 on button is applying a strong magnetic field, which helps align the protons. Then the RF pulse button sends a radio frequency pulse that interacts with those protons. When the protons relax after the pulse, they produce the signal you see on the right. It's like nudging the protons to make a little noise, and the simulator produces that signal.
Okay, can you look at this one? This one is a previous version of the simulation where we apply main field, apply RF pulse, apply gradient, detect signal, which just flicked there briefly, could barely see it. Can you tell which one of the simulation is better, this one or the previous one we've showed?
Well, the previous simulation seemed better for visualizing the proton spins and the signal directly. This current version has a more complex setup with the gradient, which is important for creating MRI images, but it doesn't clearly show the final image generation. So for understanding the basics, the previous one might be better. This one could be useful for learning about specific components like the gradient fields.
Okay, what's the difference between the blue and the red arrows?
The blue and red arrows represent protons in different energy states. The blue ones are usually in a lower energy state, aligned with the magnetic field, and the red ones are in a higher energy state. When the RF pulse is applied, some of the blue protons can jump to the red, or higher energy state.
But is it working as expected? I don't see anything's changing when the field is applied. When we load the page and the field is applied, do you see anything's changing? Is it working correctly or not?
You're right. It doesn't seem to be aligning the protons quite as expected when the field is applied. Based on what I'm seeing, the protons aren't snapping into the alignment with the B0 field the way they should. It looks like there might be a little glitch in the simulation. In a proper MRI sequence, you'd see more of those blue arrows pointing downwards when the main field is on.
Okay, let's check the original prompt. Let's see, one
Okay.
sec. Yeah, so I have this original
Got
prompt.
All right, I have the original prompt again. It seems the simulation isn't quite perfectly aligning the protons with the B0 field as described in the ideal scenario. In a real MRI, most of the protons would align with the field, leading to more blue arrows pointing downwards. the simulation isn't quite showing that strong alignment initially.
Eventually, they do seem to align, do they?
Yes, over time, you do see more of the protons aligning with the magnetic field, which is what happens in a real MRI. They gradually settle into the lower energy state, aligning with the B0 field. So the alignment does happen eventually, though it might not be instantaneous in the simulation.
Doesn't an alignment happening much faster considering the strength of the magnetic field?
You'd expect the alignment to happen much faster with a strong magnetic field, almost instantaneous in an ideal scenario. The simulation appears to be slowing down that process, so it's not perfectly representing the immediate alignment you'd expect in a strong magnetic field.
Well, that's a problem in the simulation because then it doesn't actually look like something is happening when the magnetic field is turned on.
You're right, it doesn't make it harder to see the immediate effect of the magnetic field if the alignment is happening so slowly. Ideally, the simulation should show a more noticeable alignment of the protons when the B0 field is turned on. This would better reflect the actual physics of MRI. That sounds like a great way to educate people about MRI principles. I can definitely create a single-page interactive web application for that. It will include visualizations of proton alignment, RF pulses, and signal detection, along with interactive.
So we already used that prompt to generate this web application, but there's obviously some problems with it. Can you actually summarize the prompt and suggest any improvements? Just a quick response.
Sure. The prompt requested a single-page interactive web app to teach about MRI principles, visualizing proton alignment, RF pulses, and signal generation. It needed interactive controls, sonification, and a play demo button. An improvement could be to ensure the proton alignment with the magnetic field appears more immediate and accurate when the B0 field is applied, to better reflect the actual physics.
Okay, so just again in a more critical response, how would you improve this web application that you're currently looking at?
To improve the current web application, it should make the proton alignment with the B0 field appear more immediate and pronounced when the field is turned on, aligning more closely with how it actually behaves in MRI. Additionally, ensuring the simulation accurately reflects the speed of relaxation after the RF pulse would improve the educational accuracy.
Yeah, also everything we do, we eventually publish on BioniChaos.com.
Okay, so the plan is to publish all the interactive simulations and educational content you create on the BioniChaos.com website. That's a good platform for sharing these interactive resources with a broader audience.
Yeah, so that we have been publishing stuff on this website for the last 2.5 years.
That's good to know. Consistently publishing interactive content there for the last 2.5 years builds a valuable resource for users interested in biomedical simulations and education.
Okay, so I have a bunch of MRI simulators in one. Can you look at this one as well?
Sure, I can take a look at that MRI simulator. Please show me the interface and its features, and I can provide feedback on its interactivity, educational value, and accuracy.
Can you see it on the screen?
Yes, I can see the MRI synthetic brain generator on the screen. It looks like it displays different views of a synthetic brain and has controls for the slice view, showing pathology, and a play demo function. I can provide feedback on the simulators as well.
Actually generating the data within the browser. It's obviously like a simplified thing. Can show pathology. There was something in pathology before. Remember, yeah, there it is. Well, there's something there. Hey, can you explain what you're looking at?
Certainly. The simulator is generating synthetic brain MRI images directly in the browser. It allows you to view different slices in axial, coronal, and sagittal views. The Show Pathology button introduces simulated abnormalities into the images, demonstrating how pathologies might appear on an MRI scan. This is a simplified representation for educational purposes.
Hey, can you describe the image itself?
The image displayed is a cross-section of a synthetic brain. It shows different tissue types, represented by varying shades of gray, similar to a real MRI. When pathology is shown, you can see simulated abnormalities, which appear as distinct areas with different brightness levels compared to the surrounding tissue.
Okay, and how is it relevant to the MRI simulation we're looking at before?
This interactive MRI simulator helps understand the underlying principles of MRI. It visualizes the behavior of proton spins in a magnetic field and the effect of RF pulses, which are fundamental concepts in generating the kind of images you saw in the synthetic brain simulator.
How do we link the two simulations?
You can link the two simulations by explaining that the interactive MRI simulator demonstrates the basic principles of how MRI works by showing the manipulation of proton spins. This knowledge is then applied to understand how the synthetic brain simulator generates realistic MRI images by simulating the response of different tissues to magnetic fields and RF pulses. Together, they provide a comprehensive understanding of both the principles and the application of MRI technology. Based on the concepts demonstrated in the interactive MRI simulator,
Hey, can you do more conversational responses? So I shared the original prompt that we used to generate this web application. Hey, can you just summarize it and potentially rewrite it based on our discussion above?
certainly, based on our discussion and the prompt you shared, the goal is to create a single-page interactive web application that educates users about MRI principles. The application should visually demonstrate how hydrogen atoms align with a magnetic field, respond to radio frequency pulses, and emit signals. It needs to be interactive, allowing users to adjust parameters and see real-time changes. The interface should be user-friendly, accessible via keyboard, mouse, and touch, and include sonification with a toggle. The layout should work well on all screen sizes. Additionally, a play demo button should be included to showcase the simulation's capabilities by cycling through predefined functions. The revised prompt emphasizes the conversational and educational nature of the application.
Okay, we're not getting much further. Let's finish this stream because this stream is already 3.7 gigabyte in the browser window. It's like, yeah, to know, isn't it? I don't know why it's keeping all the videos, not just converting them into tokens, because it's meant to convert it to 258 tokens per image at 1 hertz at 1 frame per second. But it doesn't actually do it. Let's pop that. Yeah, I'm meant to be creating the image as well, which is not happening at the moment. It's not happening at the moment. Yeah, it's not quite clear what's cannot apply ref clause B, all field is off. I don't know if it's accurate. Do we have any MRI experts in the room? And what's the flip doing? Yeah, we need a better prompt. That's my point. Then we get one of those reasoning models. So we're using Claude, Gemini, anything under the sun. Should we try one of those R1? Well, let's not get too excited with the models. Eventually we'll be fixing it in Visual Studio Code with Copilot, where we also have access to GPT, Claude, Gemini, all 3 or 4. So question is, should we just continue from this code or start a new one? We need someone explaining this to us properly as well. Let's do Claude. Yeah, I'm not sure about the image itself, as in how difficult. So we're currently looking at multiple simulators. I mean, this one is the clearest, the most reasonable. Well, because it's already giving you the output image. And yes, it's with the simulation can show some abnormality in the brain. So it's actually generated in the browser. The image is generated in the browser. There's some specific noise function that makes that. By the way, everything we do is available on BioniChaos.com. Go check it out, provide your feedback. Now, hopefully we have a better prompt. Let's give it to Claude for a sec. Can we resume the stream? I don't know if you can see. Can you see the screen? No. Hey, can you see the screen? No.
Yes, I can see the screen. It shows the single-page interactive web application for educating about MRI principles. I can see the simulation area, interactive controls, and the text at the bottom providing overview, instructions, and future directions.
That's not the screen we're talking about. One sec. We're talking about this one here.
Ah, I see. Now you are showing the MRI synthetic brain generator. This simulator focuses on generating realistic MRI images of a brain, allowing you to view different slices and perspectives. It complements the interactive MRI simulator by showing the final output of MRI technology, which is the ability to create detailed images of internal structures.
Did you have any ideas how do we link it to the previous simulation? How do we combine them into one, where you can actually see the final image? So you have something like this, like what you can see on the screen, that you can briefly describe, but then we also want to see the actual output result that looks like an image, similar to this. Is that possible at all? What do you think?
Yes, absolutely. We can combine the concepts from both simulators into a single integrated web application. The application could start with the interactive proton spin simulation, allowing users to manipulate magnetic fields and RF pulses. Then, as the simulation progresses, it could transition to show the resulting MRI image of a brain, similar to what you see in the synthetic brain.
Any chance it can be a single page though?
Yes, it can definitely be a single-page web application. The simulation and the image display can be integrated into a single page, perhaps with different sections or tabs to navigate between the proton spin simulation and the resulting brain image.
Yeah, we don't like tabs. I'm thinking, yeah, just a single page that, yeah, toggles. Yeah, we don't want to toggle. Why do we need the ref to show the ref pulse? That doesn't seem to do much. Can we just show, like, on the left side, how the actual physics of the magnetic field and the RF pulse work, and on the right show the resulting image?
Okay, I understand. We can create a single-page application with the proton spin simulation on the left side, visually demonstrating the effects of the magnetic field and RF pulses. On the right side, we can display the resulting MRI image, showing how the simulated spins translate into image. This setup would provide a direct connection between the principles and the resulting image, making it more intuitive and educational.
Okay, can you actually rewrite and update the original prompt we had?
Sure, I can update the prompt for you. Based on our discussion, the updated prompt would be to create a single-page web application that simulates the fundamental principles of MRI. The application should show the proton spin simulation on the left side, illustrating the physics of magnetic fields and RF pulses. On the right side, it should display the resulting MRI image, demonstrating how the spins are translated into a visual output. The interface should be interactive and provide controls for the simulation, all within a single web page.
Yeah, okay, I suspect we might need more details for it to be a standalone prompt. Can you do all the details, make it standalone so we can send it directly to the developer?
All right, let's create a comprehensive prompt with all the necessary details. Here's a standalone prompt you can send to the developer. Develop a single-page web application that simulates the fundamental principles of magnetic resonance imaging, MRI. The application should have two main sections. On the left side, visualize the proton spin simulation to illustrate the physics of magnetic fields and RF pulses. On the right side, display the resulting MRI image showing how the simulated spins are translated into an image. The application should provide interactive controls for adjusting parameters and observing their effects on both the simulation and the final image. Ensure the interface is user-friendly and provides a clear understanding of the MRI process. This prompt clearly outlines the requirements for the single-page web application.
Yeah, why do I suspect we are missing some important details?
You're right. We can enhance the prompt by adding more specific details about the functionality and features. Let's include details about the interactive controls, the specific visualizations required, and any other essential aspects. Here's a more detailed prompt. Develop a single-page web application that provides an interactive simulation of the fundamental principles of magnetic resonance imaging, MRI. The application should have two distinct sections. The left side will display a real-time simulation of proton spins, visually representing their behavior under the influence of a strong magnetic field and RF pulses. The simulation should allow users to observe the effects of different parameters, such as magnetic field strength and RF pulse intensity. The right side will display the corresponding MRI image, dynamically updating to reflect the changes in the simulation. The application should provide interactive controls, such as sliders and buttons, to manipulate the simulation parameters and observe their direct impact on the MRI image. The user interface should be intuitive and clearly display the relationship between the proton spins, the applied fields, and the resulting MRI image. The application should be developed using web technologies to ensure it runs smoothly on a single web page.
Okay, just last thing, can you comment on in the image, are we talking slices, and would we be able to scroll through the slices the simulation on the left have generated? And our question is what the link would be between the left and right, so the physics and the actual resulting image. Are we actually placing a sample that will then correspond to the image that we're actually imaging?
Yes, the image on the right side can represent slices of the simulated brain to tissue. Users can have the opportunity to scroll through different slices, providing a more comprehensive view of the internal structure. The link between the left and right sides is crucial. The parameters adjusted in the proton spin simulation directly influence the resulting MRI image. For example, changes in the magnetic field strength or RF pulse sequences will be reflected in the contrast or clarity of the MRI image. This allows users to understand the direct correlation between the physics of MRI and the final image produced, demonstrating how different parameters affect the image quality and contrast.
Okay, we really have to close this chat because it's a whopping 6.2 gigabytes. That's because it's saving all the videos. So while I'm talking, it's actually recording the screen, and then it's saving it all in the browser for whatever reason. I don't understand why it's not just turning them into tokens and just keeping it as text. Can you actually delete? You can download the videos, but you cannot delete them. I mean, you can refresh the page, obviously, but that kind of defeats the purpose. Anyhow, okay, we have a long prompt, very long prompt. Let's give it, what are we giving it to? Let's do Gemini again. A 2.5 Pro. Sounds like bro. Don't call me bro. You get a timeout. Yesterday we had to time someone out. Someone was making legit comments. Problem is using ads, words a lot. But I'm sure the comments were genuine, so that's a bit unfortunate. Should we give it to Claude as well? Claudette. Should we give it to Claudette? Let's give it to Sonnet 4. Are we just wasting electricity? Someone's saying like it's using whatever bottles of water. I mean, okay. I'm paying cents for it. If it does cost a bottle of water every time you prompt or something, what does it mean for the economy? Well, I just found a wormhole where We can generate bottles of water by paying a few cents. I don't know. Is it possible? You would think not, but I'm not an economist. I mean, how much water manufacturers, how much does it cost to water manufacturers actually make a single bottle of water? It's probably is in the cents. I don't know. Yeah, economy sometimes very surprising, isn't it? Guess we have MRI sim. Shall we pop it into a new version? Yes, let's do. That one is actually not a simulator, it's more like a synthetic synthesizer thing. So it's called MRI synth. Then we have MRI sim. Then we have MRI sim, whatever, 2.0. We have the synthesizer. Yeah, so as you can imagine, there will be a lot of MRI stuff coming your way. Beware. Beware. What should we call this one? Sim 3. Isn't there a Sim 3, the game? I think there is. Okay, now this one. Let's try the Gemini code first. 727. Can't even say numbers properly. A live server. Okay, so we have another simulator, which hopefully will combine this one. We don't really need the RF pulse, I think. We do want to see the resulting image. So in this case, the sliders don't do anything. Okay. Ooh, just happened? Had the thing flashed. Okay. So what am I supposed to flash it all the time? Is that a sound MRI actually makes? I actually have been in an MRI machine. It was a fMRI, a functional MRI. For experimental reasons. Funny enough, they get you to sign all these consent forms. You know, just in case they discover something. No, I don't want to blame and shame, but the person who did the MRI thing actually told me that they will send me the raw data. And guess what happened? They never did. They never did. Should we do a blame and shame? Reset, reset, reset. So that meant to be the sample though, isn't it? Brain slice. Well, the image should kind of stay there. Okay, it's nice. It's nice. I understand it's kind of clearer what's going on. RF pulse intensity. How does it affect? Yeah, you get the dimmer kind of image when the RF pulse intensity is low. When it's high, I get a clearer image. The protons spin and then go back to normal. It's something weird with the sound. Like, I mean, it does this ding, which I think, have anyone done an MRI scan? Is it the sound that it makes? I don't actually remember hearing any sounds when the MRI machine. I think I was doing like math tasks or something, so I probably wasn't paying attention to the sound. Oh, that's nice. The sound actually changes. Oh, there's like 3 protons in there, overlaid on top of one another. On top of one another. A field strength. Ooh, can go from 0.5 whatever Tesla all the way up to 3 Tesla. Well, now I mean it's a simulation. Why not go all the way up to like what's that, 7, 8, 9 Tesla? I like it. I don't like the fact that the image doesn't actually stay put, where you could actually, because there's no way for you to actually play demo. So demo is don't take my job, please. Got laid off with 3 kids, a daughter, 1 son. Don't take my job. Yeah. Too late. Sorry. Why is the play demo not actually doing the imaging? It's not actually pressing so the demo mode, all it should do is just go through a sequence as if I was demoing the web application, but it's not doing it. It's doing the slices, but it's not actually pressing the apply ref. Am I supposed to do it myself? Surely not. Am I supposed to click buttons with an actual mouse and finger? It's crazy. What are you talking about? Play demo should just do it for you and should run continuously. So we pop some music on top of it, or do the sound that we have, and just generate a gazillion of YouTube videos that go viral and get millions of dollars out of it. So that should give you the job back that you're talking about. Because what job? You're saying, don't take AI, don't take my job. Please, got laid off with 3 kids. Well, what job was it anyway? Clicking a mouse and keyboard. Let's see. And we haven't improved it actually. Okay, anyway, we have 3 versions of it. So we have that one. We had an old version, which, it's trying to publish, obviously. We should just get rid of it. By the way, everything we do, we do it for you. It's available on BioniChaos.com. Go check it out. And provide your questions, comments, complaints. Yes, we have complaints about the colors, but if you're actually complaining about something, then make a suggestion on how to improve it. Is Hodgkin-Huxley action potential simulator relevant to MRI? Well, it should, but I don't know how to actually link it together. It doesn't actually fit the screen. We have to put it full screen. Pop the thing in the chat. Yes, we can apply stimulation by pressing the apply stimulus button. Then you see an action potential. An action potential, then it shouldn't let you fire another action potential for a while, unless the channels they recover the potassium and whatever other channel. You have all the explanation at the bottom. So forget what the channel is: sodium and potassium. Which one is which? Sodium and potassium. And once they recover, you can fire again. Poof. You can set different parameters. So that's the kind of type of simulations we make. So don't forget to smash that like button. Yeah, magnet simulations. Well, that was kind of obvious. A thing to do, even though it's actually did a pretty decent job. So you can learn a lot about magnetic fields. For that reason, it will only let you maximum of 4 magnets are allowed. Big no. You ask for more than 4 magnets. So the simulation flips out. We can fix it later if that's a big problem, but obviously leave it as is for now. yeah, we were doing what were we doing? MRI simulation. Well, I mean, it's related to action potentials because that's what you're recording in MRI, hopefully. Well, actually not. So it's actually not recording brain activity. Surprise, surprise. It's actually recording this quantum physics, whatever experiment of proton spin of electrons, protons, and then hopefully you're able to recover something useful. Obviously, not getting an image out of it. It's just a sensor, whatever, a radio frequency, magnetic frequency, like sensor, and then it gets reconstructed into an image. So here we actually show how the whole thing works. And I'm not an MRI expert. If there are any experts listening to this, do let us know. Let us know if this is correct at all or not. What's up with this? Okay, so you can actually use the slices. It's not very intuitive. I mean, if the image is just staying there, don't want like more controls to it or something, do we? Do we? Do we want more controls or not? Do we want more controls? Okay, we had the Claude making something. Did it finish the code? No, it didn't finish the code. That's why I don't see anything. To finish the code. Claude is normally not lazy. I still have 6 gigabyte. How do you clear? Yeah, I'll have to start a new conversation. So I've been talking for too long. So let's share the screen. Share the screen. We have a prompt engineer. Hey, can you explain what's on the screen real quick? Make it fun, critical. Don't mind the dark humor.
All right, picture this. On the left, you've got these tiny little protons acting like they're at a chaotic proton party, and the B0 field is like this super strict bouncer trying to get them all in line. Then you hit the RF pulse, and it's like blasting music that makes them all start dancing in a crazy synchronized way. On the right, that black screen is like the empty canvas of an abstract dance performance. When the music stops, the protons start to chill out, and as they settle down, they emit these little signals that gradually form an image, kind of like the echoes of their dance moves. It's a strange ballet of physics, turning invisible movements into these intricate pictures. Pretty wild, huh?
Pretty wild, huh? Do we have... I don't know if a Claude made a similar simulation. Did it actually finish the code? No, it did not. Oh, Claude didn't finish the code. Claude didn't finish the code. We have now a simulation. I can imagine there will be lots of them coming. Actually, I had a newer version of this where you have two neurons talking to one another. Kind of working. Yeah, I can test the previous version as well. Just take a 5-minute break. Pop some AI, obviously AI music. There we go. AI test kitchen. Music effects DJ. A huge drop reggae ADM. Not sure about that. Let's try to fix this or not. Let's reduce the chaos a bit. Pop your questions in the chat. I'll be back in 5 minutes. Oh, it's still playing. That's a good sign. Can change it a bit. Do we need the background music or not? The quality is simple. The quality any better? We're actually trying to make our own music generators as well. That didn't work well. I mean, it's still up and running. I have it on the side somewhere. Yeah, it's not working well. We we did it like a year ago or so we can try it. I've redoing the code with better models. Obviously, music is also relevant to biomedical data. Get a lot of neuroscience experiments and things done with music. Any questions in the chat? No. I had a few subscribers. Thank you very much. Again, that music is annoying. Well, first of all, it's out of tune. Maybe it's because we were combining reggae and acoustical instruments. We think, no, it's still in tune. It's still out of tune. Now when you have bouzouki acoustical instruments. Bouzouki, mandolin, and reggae. How's that for a combination? Okay, mandolin. Get rid of it, get rid. Reggae. Still reggae 50-50. Okay, we're going places now. We are going places. Drumline, harp, and cello punk song. Okay, I have to try that one out. Yeah, it's an okay background, isn't it?
Hey everyone! So you're looking at the BioniChaos website right now. It's got these cool interactive tools for exploring things like quantum mechanics, neuron behavior, and even looking at retinal images. It's pretty neat for anyone interested in biomedical engineering or neuroscience. I'd totally recommend checking it out and letting the creators know what you think. Your feedback could really help them improve these tools. Oh, cool. Now you're seeing a few more tools on the website. There's one for visualizing physiological signals, another for simulating brain stimulation, and even one where you can mess with neuron properties. Plus, there's a spectrogram generator and a brain EEG simulation. It seems like a really comprehensive set of tools for anyone interested in this kind of stuff. Seriously, give it a look and let the developers know what you think. They'd love to hear your feedback to make these tools even better. Awesome. Scrolling down, you can see even more tool stuff. There's a Fourier series visualization, and then something really interesting about AI understanding causality, which is a big deal in AI right now. And they've got a high fidelity Fourier series simulation too. This website offers some amazing tools for visualizing complex concepts in biomedical engineering and neuroscience. Seriously, dive in and check them out. Your feedback is really valuable to the creators, helping them make these tools even better for everyone. Let them know which tools you find most helpful or interesting. Wow, look at all these tools. We've got this interactive report on the multimodal medical data landscape. That sounds super insightful for anyone looking at health data. And then there's an interactive guide to EEG technologies. Wondering how that breaks down those complex concepts. Plus, a visual analysis of Cochlear Limited. That could be really interesting for understanding the impact of medical technology. And look, there's a neurofeedback interactive evidence review too. These tools offer some incredible ways to explore medical data and technology. I'm curious, which of these interactive experiences seems the most engaging to you? And what kind of insights do you hope to get from them? Your thoughts would be super helpful for the developers, so definitely let them know what you think. Look at these. Now we're seeing even more interactive tools. There's an evidence review for neurofeedback. Curious about the latest research on that, huh? And then there's an AI-powered EEG speech decoding tool. Imagine the possibilities for communication. Plus, a modality comparison chart, which could be super helpful for understanding different measurement methods. And don't forget the Cochlear Simulator and Advanced EEG Simulator. Amazing for learning and experimenting. Seriously, these tools offer so many unique ways to engage with complex information. What aspects of these simulations are you most excited to explore? And how do you think they could help you understand these topics better? Your feedback is super valuable to the developers, so don't hesitate to share your thoughts. Wow, the BioniChaos website has so many fascinating tools. We've got an interactive evidence review for epilepsy and cardiac health, really digging into that complex relationship. And then there's a synthetic noise generator dashboard, perfect for experimenting with different signal types. Plus, an interactive explorer for public multimodal biomedical datasets. That's a goldmine for researchers. And an ECG simulator and FNARS interactive viewer add even more incredible capabilities. It's amazing how many different areas these tools cover. Have you found any particular tools that sparked your curiosity the most? And what kind of possibilities do you see for using these interactive features in your learning or research? Your feedback is incredibly valuable to the creators, so please do share your thoughts and help them make these tools even more impactful. These tools are just incredible. Now we're seeing an interactive cochlear implant simulator. How amazing to explore that technology. And then there's Rhythm Scan for analyzing EEG data and detecting seizures with machine learning. That's a powerful combination. Plus, a joint time-frequency scattering tool for seizure detection adds another advanced approach. And the Seer Medical Interactive Case Study provides a real-world perspective. Finally, the EEG device comparison is super helpful for evaluating different devices. These tools really demonstrate the incredible diversity in biomedical technology and analysis. What kind of insights do you hope to gain from exploring these particular tools? And which ones seem the most relevant to your interests? Your feedback is invaluable to the developers, so please take the time to share your thoughts and help shape the future of these interactive resources. And the list of tools keeps getting more impressive. We have the Stentrode, a minimally invasive brain-computer interface that's groundbreaking technology. And the Biomedical Data Types Explorer is a fantastic resource for navigating different kinds of biological data. Plus, the Forecast Trap provides a critical analysis of seizure prediction technologies, which is so important. And the Hearing Aid Simulator offers a practical understanding of sound amplification. Finally, PaperViz is a fantastic tool for visualizing research papers. It's remarkable how these interactive features make complex topics so much more accessible and engaging. Which of these tools do you think would be most beneficial for your learning experience? And what kind of unique insights do you hope to gain from interacting with them? Your feedback is incredibly valuable to the developers, so please share your thoughts and help them continue to improve these amazing resources. There are some incredible tools on the BioniChaos website. We have the myoscope for visualizing EMG signals, great for exploring muscle activity, and then there's SpectraWave, a real-time audio spectrogram visualizer, fascinating for sound analysis. Plus, the biomedical fields visualization uses a Venn diagram to show the intersection of different areas, really helpful for understanding the bigger picture. And MyoMock lets you explore EMG signals through a simulator. Finally, the ChatGPT author explores the role of AI in scientific writing. It's amazing how these tools cover such a wide range of topics. Which of these interactive features do you find most intriguing? And what kinds of questions do you have about their specific functionalities? Your feedback is really valuable to the developers, so please don't hesitate to share your thoughts and help them make these resources even more helpful. This interactive MRI simulator is a fantastic addition to the BioniChaos website. It perfectly complements the other interactive tools by providing a hands-on way to understand the complex principles of MRI technology. Being able to adjust parameters like the B0 field strength and RF pulse intensity and see the resulting changes in the proton spin simulation and MRI image is an incredibly effective way to learn. It's like having a mini MRI scanner at your fingertips. This interactive approach really helps demystify a complex medical imaging technique. What kind of features did you find most helpful in understanding the process? And are there any other aspects you'd like to see integrated into the simulator? Your feedback is crucial for the developers to make this tool even more effective and user-friendly. Don't hesitate to share your suggestions. Based on the context of the interactive MRI simulator, I would expect the Play Demo button to initiate a demonstration that walks you through the key steps of an MRI scan. It would likely show how the different parameters, like the magnetic field strength and the RF pulse intensity, affect the proton spin simulation and ultimately contribute to the generated MRI image. It would basically provide a guided demonstration of the simulator's capabilities, making it easier to understand the relationship between the settings and the resulting image. Sure, the text says, how to use. The application is split into two main parts, the simulation on the left and the resulting image on the right. The goal is to see how your actions in the simulation panel directly affect the generated MRI image. Proton spin simulation, left. This canvas shows a group of proton spins, the small arrows. In their natural state, they are randomly aligned. Use the B0 field strength slider to apply a strong external magnetic field. Notice how the protons align with the field and begin to precess or wobble around the field's axis. A stronger field, higher Tesla, T, results in a faster precession. The RF pulse intensity slider sets the flip angle of the radio frequency pulse. A 90-degree pulse will tip the spins fully into the transverse plane. Click Apply RF Pulse to excite the protons. You will see them tip over and spin in unison, in phase. This synchronized spinning generates the detectable MR signal. After the pulse, the spins will gradually dephase, spread out, and return to their original alignment. This is known as T2 and T1 relaxation. Resulting MRI image, right. This canvas displays a slice of a synthetic brain. The brightness of each pixel depends on the MR signal intensity from the corresponding region in the simulation. Ah, I see. It seems like the demo is designed to showcase the adjustments of the B0 field and the RF pulse intensity, demonstrating how these settings influence the proton spin simulation. However, it isn't programmed to actually apply the RF pulse in the simulation at each step, which is why you don't see the resulting MRI image change dynamically. The demo seems focused on illustrating the relationship between the field strength, pulse intensity, and the initial proton spin behavior, rather than completing the entire MRI imaging process. It's a way to understand the individual settings without going through the full imaging sequence. This can be helpful for learning the fundamentals before experiencing the complete simulation. It appears there might be a misunderstanding or a discrepancy between the intended functionality and the actual behavior of the demo. While the demo does adjust the B0 field strength and the RF pulse intensity, it doesn't seem to be activating the Apply RF Pulse button, which is the necessary step to trigger the proton spin response and generate the MRI image. Therefore, even though the parameters are changing, the core interaction that leads to the image formation is not being demonstrated. The user would need to manually click the Apply RF Pulse button to see the full effect of the simulation and generate the corresponding image. This suggests that the demo is either missing complete or intended to focus on specific aspects of the simulation rather than the full imaging process. Thank you for the clarification. Based on the code's explanation, it appears that the Apply RF Pulse function is indeed being called. I understand your concern. If the simulation is not displaying the expected image despite the code calling the Apply RF Pulse function, there could be other issues affecting the visualization. This might involve animation timing, rendering glitches, or other factors within the simulation logic. It would be helpful to review the code further, particularly the parts related to the animation process and the display of the MRI image. to identify the specific issue preventing the visual updates. Testing the code again with close attention to these aspects should help pinpoint the problem. Thank you for the precise diagnosis. The developer's feedback clarifies that the if RF pulse intensity return function within the apply RF pulse function is indeed preventing the RF pulse from being applied during the demo, thus causing the MRI image not to update. Removing or adjusting that line would allow the demo to function correctly, triggering the RF pulse and the corresponding image updates as intended. If you would like me to make the necessary changes, please let me know.
Okay, so I actually had Gemini talking to ChatGPT and actually fixed the problem together. So one can actually view what's on the screen. We described the problem briefly and actually summarized it for the developer. The demo mode wasn't working correctly. So when changing stuff, it wasn't actually applying the RF pulse before. Now it does. So it will change something, apply the RF pulse so you can actually see the image. Okay, so now it's actually working correctly. If you can quickly summarize, but also, do you think we can run the demo continuously for it not to stop? How would you go about it?
Now that the apply RF pulse function is correctly triggered during the demo, the simulation should now display.
Keep going.
Right. To run the demo continuously, you can modify the demo logic so that it automatically triggers the RF pulse sequence at regular intervals. One way to do this is to set up a repeating timer or loop.
Snap. AI Studio just snapped on me. Something went wrong. Well, ooh, the browser page, the tab has like 11.3 gigabyte of memory usage. Ah, this is crazy. I don't know why it's so inefficient. I don't know why it's so inefficient. It's not meant to. It's just because it's recording the whole thing. Okay, so this is working really well now. Can you just very briefly review in a conversational text what the changes were made?
The changes involved ensuring the apply RF pulse function works during the demo by removing the if is demo running return condition. This allowed the demo to trigger RF pulses and dynamically update the MRI image as intended, aligning the functionality with the expected behavior.
Okay, this is great. So it's working now perfectly well. Thank you very much. Now, how would you go about running the demo mode continuously for it not to stop unless the user is interacting with the page or pressing the play demo button again or something?
To make the demo mode run continuously until the user interacts with the page or presses the play demo button again, you can modify the run demo function to loop indefinitely. Here's
No, can you just do a conversational quick response without any code? We're just talking about it for now, not modifying the code yet. So when we're playing the demo, first of all, we want it to be continuous, but second, we want the parameters to adjust to be different parameters. So it's essentially be continuously showing how the application is working, but potentially maybe not just looping through the same cycle, but just modify or making the cycle longer. What do you think? Just a conversational quick response, no code, no bullet points.
That sounds like a great idea. Making the demo continuous while varying the parameters over time would make it more dynamic and engaging. Instead of looping through the same fixed sequence, you could introduce randomness or gradual changes to parameters like the B field strength, RF pulse intensity, or brain slice. This way, the demo would feel more like an ongoing exploration of the simulator's capabilities rather than a repetitive cycle. You could even incorporate pauses or transitions to highlight specific effects, making it more educational and visually interesting. It would essentially turn the demo into a live showcase of the application's functionality, keeping users engaged while still allowing them to stop it or
Okay, so how would you practically go about it, modifying the code? Again, just conversational response.
To make the demo continuous and more dynamic, I would modify the run demo function to include a loop that keeps running until the user stops it. Instead of repeating the same sequence, I'd introduce variations in the parameters, like randomizing or gradually changing the B field strength, RF pulse intensity, and brain slice. This would make the demo feel more like a live, evolving showcase. To implement this, I'd use a while loop that checks if the demo is still running. Inside the loop, I'd adjust the parameters dynamically, perhaps using random values within a range or smoothly transitioning between values.
Okay, that sounds good. Can you actually modify the code? Just go ahead and modify the code to make the demo mode continuous as discussed, and just comment along in conversational style what changes are made to the code. Take your time.
Made changes. The code is now updated so the demo mode runs continuously, picking new random values for the MRI parameters each cycle. You can stop the demo at any time by clicking the Stop Demo button, which toggles back to play demo when stopped. Conversational comments have been added in the code to explain these changes and the new dynamic behavior. Absolutely. Here's how the new demo works, in a conversational way. Now, when you hit the play demo button, the simulator goes into a continuous demo mode. Instead of just repeating the same steps, it randomly changes the three main parameters, B field strength, RF pulse intensity, and the brain slice each cycle. So, you'll see the magnetic field strength slider move to a new value, the RF pulse intensity change, and the brain slice jump to a different section, all automatically. After each adjustment, the demo applies an RF pulse so you can see the effect on the proton spins and the MRI image. This keeps going, with new random values each time, until you click the button again to stop the demo. It's like a live, ever-changing showcase of what the simulator can do. Sure. Let's dive into how this updated demo works and critically evaluate its behavior. So, the demo now runs continuously, which is great for showcasing the simulator's capabilities. It dynamically adjusts the B field strength, RF pulse intensity, and brain slice, all while applying RF pulses and updating the MRI image. This creates a live, evolving demonstration that feels more engaging and less repetitive. The randomness in parameter selection adds variety, making it feel like a real exploration of the simulator. However, there are a few things to consider critically. First, how smooth is the transition between parameter changes? For example, when the B field strength slider moves, does it feel natural or does it jump too quickly? The animate slider function should ensure smooth transitions, but if the duration is too short, it might feel abrupt. Similarly, the pauses between actions, like waiting for the RF pulse to relax, need to be balanced. Too short, and the demo feels rushed. Too long, and it might lose the user's attention. Another question is about the randomness of the parameters. While randomization adds variety, does it always produce meaningful or educational results? For instance, if the RF pulse intensity is set to a very low value, the resulting MRI image might not change much, which could confuse users. It might be worth constraining the randomness to ensure that each cycle demonstrates a clear effect, like always including a 90 degrees pulse at some point. Then there's the issue of user control. The demo stops when the user clicks the button again, but what happens if they interact with the sliders or other controls while the demo is running? Does the demo override their input, or does it pause to let them explore manually? It might be helpful to disable manual controls during the demo or provide a clear way to switch between demo and manual modes. Lastly, let's think about the educational value. Does the demo explain what's happening as it runs? For example, when the B field strength increases, does the user understand that this speeds up the precession of the proton spins? Adding some on-screen text or tooltips to explain each step could make the demo more informative, especially for first-time users. In terms of potential issues, one concern is performance. Since the demo runs continuously, does it put too much strain on the browser, especially with the animations and canvas rendering? If the frame rate drops, the demo might feel sluggish, which could detract from the experience. Testing on different devices and browsers would be important to ensure smooth performance. Overall, the continuous demo is a fantastic improvement, but there's room to refine the user experience, ensure clarity in the educational goals, and address potential edge cases. What do you think? Are there specific areas you'd like to focus on improving further?
What do you think? I think it's working great. I don't know. Yeah, we did ask it to critique the thing, but which it did, but yeah, we could add the annotations. Just a quick conversational response about just moving on onto the talking about the annotations. So during demo mode, what kind of annotations would you display, and where would you display them, not to obstruct the simulation?
During demo mode, annotations should be minimal yet informative, providing context without obstructing the simulation. For example, parameter changes * display a small floating label near each slider, e.g., B field 2.5T, when it changes. These labels could fade out after a few seconds to avoid clutter. Current action asterisk add a subtle overlay at the top or bottom of the screen with text like applying RF pulse or switching brain slice to explain what's happening in real time. Educational notes asterisk use a small, semi-transparent box in a corner, e.g., bottom left, to display brief educational tips, such as higher B field increases precession frequency. Interactive highlights asterisk highlight the active slider or control briefly, e.g., a glowing border, to draw attention to the parameter being adjusted. These annotations should be non-intrusive, fading in and out smoothly, and positioned away from the main canvas areas to keep the simulation visually clear. To keep the layout clean and intuitive, the two canvases, proton spin simulation and MRI image, should remain side by side, as they currently are. This allows users to easily correlate the changes in the proton spins with the resulting MRI image. If you want to add annotations or additional information, you could place them below each canvas or in a small overlay at the bottom of the respective panels, ensuring they don't obstruct the main visuals. Yes, there are a few additional constraints to consider. User interaction during demo asterisk if a user interacts with sliders or buttons while the demo is running, should their input override the demo, or should the demo temporarily pause? This needs to be clearly defined to avoid confusion. Performance on low-end devices asterisk continuous animations and updates can be resource-intensive. Ensuring the demo runs smoothly on devices with limited processing power or older browsers is important. Educational clarity asterisk while the demo showcases the simulator's features, does it clearly communicate the science behind the changes? Adding brief, non-intrusive explanations for each step might help. Randomness constraints asterisk ensure the random parameter changes always produce meaningful results. For example, avoid setting RF pulse intensity too low or switching slices too rapidly, as this might confuse users. Accessibility asterisk consider how the demo works for users with disabilities. For instance, ensure annotations are screen reader friendly and that the interface is navigable via keyboard. These constraints can help refine the demo and make it more robust and user friendly.
Okay, so we're going for the Okay, can we start introducing the annotations during demo mode? There is some space below the two canvases, essentially below the simulation and above, so essentially between the simulation and the text.
Yes, you can definitely introduce annotations during demo mode in that space. The area below the two canvases, between the simulation panels and the info section, is a perfect spot for displaying dynamic annotation messages. This way, the annotations won't cover the visualizations, but will still be highly visible to the user. You could add a dedicated annotation bar or box that updates with brief, clear messages about what the demo is doing, e.g., increasing B field strength to 2.5 T, applying RF pulse, 90 degree, switching to brain slice 5, etc. These messages can change in sync with each demo step, helping users follow along and understand the simulation process without cluttering the main canvases. This approach keeps the interface clean, educational, and user-friendly.
Okay, so start updating the code. That obviously might take a while. So as per usual, everything we do eventually available on BioniChaos.com. Go check it out and don't forget to provide your feedback. Okay, no, the current position of the annotations is not great. It's appearing to the side of the two canvases instead of below of them.
Made changes. The annotation bar is now positioned below the two canvases, not to the side. It will appear directly under the simulation panels and above the info section, making the annotations more visible and visually aligned with your intent.
Let's skip those changes, play simulation. Should we have the... what do you think? Should we have the sound on by default? The sound is not bad actually in this case. It's not super annoying.
Having the sound on by default could actually enhance the experience, especially since it's tied to the simulation and isn't intrusive. It gives immediate audio feedback, making the demo more immersive and helping users connect the physics to what they hear. As long as there's a clear and easy way to toggle it off, starting with sound enabled is a good choice for engagement. Most users can quickly mute it if they prefer silence.
Okay, so can we change the default for the sound to be on page load?
Made changes.
Made changes. Don't take my
The sound
job.
is now enabled by default when the page loads. The sound button will show sound on and the simulation will provide audio feedback right away, making the experience more immersive for users.
What? Wait. The sound on is on HTML, but probably somewhere in JavaScript the sound is still set to off, so I can't actually hear anything on page load. Can you check the code? Can you check the code?
Summarized conversation history. The issue seems to be that while the sound button's text and class are updated to reflect sound on by default, the actual audio context, audio CTX, and gain node might not be properly initialized or set to produce sound. I'll review the JavaScript code to ensure the sound is correctly enabled on page load. The issue lies in the setup audio and update audio functions. While the sound button is updated to on by default, the gain node's gain is not set to a non-zero value to produce sound. I'll fix this by ensuring the gain node is initialized with a default gain value when the sound is turned on. Made changes. The code has been updated to ensure the sound is actually enabled by setting the gain node's gain to a non-zero value when the sound is turned on by default. You should now hear the sound on page load. Let me know if you need further assistance.
Guess I did fix that problem, obviously. It's a simple fix. There's a couple of questions. Questions. Can you quickly look at the code? We have a couple of questions, but maybe you can. Do you have any questions? Just a conversational response, no code and no bullet points.
Sure, I've reviewed the code. It's a well-structured interactive MRI simulation with clear separation of concerns for UI, simulation logic, and rendering. The use of sliders, canvas elements, and audio feedback creates an engaging educational tool. If you have specific questions or needs,
Okay, a question about the field strength. So currently it's going from 0.5 Tesla all the way up to 3 Tesla. Can you explain this range? A conversational response?
Sure. The range of 0.5 Tesla to 3 Tesla represents the typical magnetic field strengths used in clinical MRI machines. Lower field strengths, like 0.5 Tesla, are less common today but were used in earlier MRI systems or in specific cases where lower field imaging is sufficient. Higher field strengths, like 3 Tesla, are more common in modern clinical settings because they provide better image resolution and signal-to-noise ratio. This range is a good balance for educational purposes, as it covers the most relevant field strengths without venturing into ultra-high field MRI, which is less common and primarily used in research.
Okay. Yeah, we had another subscriber. Thank you very much for subscribing. Don't forget to provide your comments as well. That's what's really getting us going. Your comments. So the thing is, okay, so just continuing from that point, so why stop at 3 Tesla? Why not go higher? Can you respond based on whatever current research?
Going beyond 3 Tesla is certainly possible and is already being explored in research in specialized clinical settings. Higher field strengths, such as 7 Tesla or even 10.5 Tesla, offer significantly improved signal-to-noise ratios and spatial resolution, which can be beneficial for detailed imaging of small structures like the hippocampus or for studying microvascular changes. However, there are practical and safety considerations that limit their widespread use. First, higher field strengths increase the risk of specific absorption rate, SAR, heating, which can pose safety concerns for patients. Additionally, the cost and complexity of building and maintaining ultra-high field MRI systems are much higher. Artifacts, such as susceptibility distortions, also become more pronounced at higher fields, which can complicate image interpretation. Finally, regulatory approvals and the need for specialized training further limit their adoption in routine clinical practice. So, while higher fields are exciting for research, 3 Tesla strikes a balance between performance, safety, and accessibility for most clinical applications.
Okay, but we are in we live in a simulation. So how would you change the slider to include the higher Tesla options? And if we do, how would it affect the actual visualization on the simulation?
If you want to include higher Tesla options in the slider, you could extend the range of the B field strength slider to, say, 7 Tesla or even higher. This would allow users to explore ultra-high field MRI scenarios. Here's how.
Can you summarize the visualization impact in a conversational style? Make it fun.
Absolutely. So, imagine cranking up the Tesla slider to 7 or beyond. Things get wild. First, the protons in the simulation would start spinning like they're on a caffeine high, thanks to the Larmor frequency skyrocketing. The canvas would be buzzing with faster, tighter precession animations, making it visually dynamic but potentially chaotic if not handled smoothly. The MRI image on the right would glow brighter, as higher field strengths mean stronger signals. But here's the twist: at ultra-high fields, artifacts might sneak in, like little visual gremlins, distorting the image. It's a trade-off, more detail but also more quirks to deal with. And the sound? Oh, it'd be like turning up the pitch on a theremin, higher and sharper, maybe even out of human hearing range. You'd need to scale it down to keep it fun and not ear-piercing. It's like giving the simulation a turbo boost but making sure it doesn't spin out of control.
Did you just mention the theremin? Can you explain what that is? Make it interesting and fun.
Yes, the terminal can be a fun and interactive way.
No, the theremin. You mentioned theremin. Can you briefly explain what it is? Make it fun.
Ah, the theremin. It's like the magical unicorn of musical instruments, because you play it without even touching it. Invented in 1920 by Lyon Theremin, it's an electronic instrument with two antennas. One controls pitch, and the other controls volume. You wave your hands near these antennas, and voila, it produces eerie, otherworldly sounds, like a sci-fi movie soundtrack or a ghost humming in the attic. It's basically the OG of electronic music, and playing it feels like conducting an invisible orchestra. If you've ever heard the spooky whir in old horror films, that's probably a theremin showing off its haunting charm.
How's it relevant to MRI imaging? Just keep it brief and fun.
The theremin is like the MRI's quirky cousin in the world of physics. Both rely on electromagnetic principles. MRI uses magnetic fields and radio waves to image your insides, while the theremin uses electromagnetic fields to create spooky, touchless music. In a way, the theremin's eerie sound could be the soundtrack to the mesmerizing proton spins in your MRI simulation.
There's no questions in the chat. Yeah, everything we do is eventually available on BioniChaos.com. You can go check it out. So essentially play with all the tools and web applications that we make straight away, all by yourself. Actually had another version of the webcam filter. Didn't make it to production, or not. Yeah, it did make it to, well, it is on the side. Can play with it as well. I'll pop the link in the chat. Yeah, if you have any comments, if you actually went even if you just went and checked the website, do let us know. We do wanna hear your opinion and what's your experience like. Yeah, made some message a new version of this. We had an old one. We made it some improvements. Yeah, the blurring wasn't efficient, so we added some more. We added hue rotation threshold, pixelation, edge detection was already there, pixelation was there. We added threshold. You can adjust your threshold. Hue rotation, yeah, they don't work really well. Channel swap. Green screen, that's actually an interesting one. It actually does work, but needs more testing. We can do more testing on it later. The blur was highly inefficient. We have a different version of it. It's this blur, and now we also calculating the processing time, FPS. So if it's setting, we have more settings at a drop-down menu. So the frame rate. Why is it 50? 30? Yeah, I can hear my CPU, GPU fans going. That shouldn't be the case. Yeah, sharpen works okay. Emboss, don't remember. Posterize, I think it works. Anyway, pixelate. Which one out of edge? Edge takes a bit more. So 7 milliseconds processing time. Pixelate's actually working better. Pixelate is working better. Anyway, go check it out. It's kind of stuff we have on the site, and it's sitting there waiting for you to try it out. Record your video with it as well, or just provide the text feedback. Actually, go back. Can we talk briefly about the fact that the brain slice is only flashing very, very quickly? I can barely see it, kind of thing. It's too fast. Can you comment on that if you have any funny comments or funny question about that? Go for it. Go for it. Otherwise, we'll lose the bot.
So the brain slices are doing their best impression of a strobe light, huh? It's like they're auditioning for a nightclub gig instead of an MRI simulator. Honestly,
Yeah, that's right.
It's a bit much. Who can process anything when the slices are flashing by like they're late for a meeting? Maybe the simulation is trying to say, blink and...
Okay, so how would you recommend improving the code to address that?
To address the issue of the brain slices flashing too quickly, I would recommend slowing down the updates to the slice slider or introducing a delay between slice changes. This can be achieved by modifying the run demo function or the
I don't think it's anything to do with the slice changes. You mean we're only displaying one slice at a time. It's nothing to do with the brain slices. You mean the scroller? No, we're currently displaying only one slice at a time. I mean, we could do just a scroll every time, like when we apply our ref pulse, instead of just showing one brain slice, we could just slice through all the, what do we currently have, 10 slices? What do you think of that? Just a quick conversational style response.
Oh, I love that idea. Instead of sticking to just one slice, you could make it feel like the RF pulse is slicing through the brain in real time. It would add a dynamic, almost cinematic effect, like flipping through the pages of a book but with brain slices. It could also help users visualize how the MRI scans multiple layers to build a full 3D image. Plus, it'd make the simulation feel more alive and interactive.
Okay, so how would you actually go about changing the code to make that work? And so we are turning off the random slice now, are we? And just adding a slice sweep every time they apply a ref button. Is wouldn't let me finish
To
talking.
implement a slice
It's
sweep
too
every
fast.
time you apply an RF pulse, instead of showing a single random slice, I would update the apply RF pulse function so that, after the pulse, the simulation automatically scrolls through all available brain slices in sequence.
Okay, can we just try it out so we know what we are talking about? Just modify the code and do a conversational response in the chat of how the code was modified.
Made changes. The code is now updated so that when you click Apply RF Pulse, the simulation automatically sweeps through all the brain slices, showing each.
Okay, I do see the sweep, but then it's not actually displaying anything. It's still displaying just the one slice, and then the scroller does the sweep, but that's not actually showing the 10 slices. Do you know what I mean?
Yes, I understand what you mean. The sweep is moving the slider, but the MRI image isn't visibly updating to show each slice as the sweep happens. This is likely because the signal strength is decaying rapidly during the sweep, so by the time later slices are shown, the image is already faded or dark. To fix this, I'll make sure that during the sweep, the signal strength is held at its maximum, or at least a visible value, for each slice, so every slice appears bright as the sweep happens. After the sweep, the normal decay can resume. I'll update the code to achieve this effect. Made changes. The code is now updated.
We need to make sure, so essentially when the apply RF pulse is being pressed, we want to make sure that we're showing essentially all the brain slices that were made with those settings, with the current settings. So we want the brain slices, the slider to move from 1 to 10, and also update the resulting MRI image. So we want to show all the slices. Do you understand what I mean?
Yes, I understand exactly what you mean. When the RF pulse is applied, you want the simulation to sweep through all the brain slices, and for each step, the MRI image on the right should update to show the corresponding slice, so users actually see all 10 different slices, not just the slider moving. The previous code tried to do this, but the main animation loop was still running and would quickly overwrite the image, or the sweep was not visually clear. To fix this, I'll ensure that during the sweep, the MRI image is updated for each slice and remains visible long enough for users to see each one. After the sweep, the simulation will return to normal. I'll update the code so that the MRI image is always in sync with the current slice during the sweep, and the sweep is visually clear and not interrupted.
Okay, it's working really well now. So now in demo mode, we don't need to randomly change the brain slices anymore, do we? Can you explain that bit? And modify the code if you can. You understand what we're talking about?
Now that the RF pulse automatically sweeps through all the brain slices and displays each one, there's no need for the demo mode to randomly select and display a single brain slice anymore. The sweep itself already gives users a clear, animated view of all slices, making the random slice change redundant and potentially confusing. I'll update the demo mode so it no longer randomly selects a brain slice. Instead, it will let the RF pulse sweep handle the slice display, keeping the demo focused and visually consistent. Made changes. The demo mode has been updated so it no longer randomly selects and displays a single brain slice. Now, when the demo runs, the RF pulse sweep will handle showing all the slices in sequence, making the experience smoother and more intuitive for users. This keeps
Okay, this seemed to work really well now. Now another thing, just moving on, the demo. Can we start the demo when the page loads, or would it cause any other issues? What do you think?
Starting the demo automatically when the page loads is definitely possible and should work smoothly, especially now that the demo is visually clear and doesn't require user input to get started.
Okay, so if starting the demo when the page loads wouldn't cause any trouble, can you just modify the code to start the demo automatically on page load?
Made changes. The code is now set to automatically start the demo about 1 second after the page loads. This means users will see the interactive demo in action right away, but they can still stop it at any time using the Stop Demo button. This should make the experience more engaging from the moment the page opens. The sound logic is present and should work, but with the demo now starting automatically, some browsers, especially Chrome and others with strict autoplay policies, may block audio playback until the user interacts with the page, like clicking anywhere or pressing a button. This is a common browser restriction to prevent unwanted sounds. If the sound is not playing automatically, it's likely due to this autoplay policy. Once the user clicks the sound button or interacts with the page, the audio context should resume and sound will work as expected. If you want to improve the user experience, you could display a message or visually prompt users to click anywhere to enable sound if the audio context is suspended. Would you like me to add a friendly prompt for this scenario?
No, I don't want a prompt for that scenario, but currently it seems like, yeah, I understand what's happening, but currently it still seems so the sound is on when the page load, the animation is already started, but then even after user interaction, when I click on the screen, the sound is still off at the moment. Can you explain why that might be? Just a quick response.
Summarized conversation history. The most likely reason is that the audio context is created and started before any user interaction, so browsers, especially Chrome and Safari, keep it in the suspended state due to autoplay restrictions. Even after user interaction, like clicking, your code does not explicitly call audio.ctx.resume, unless the user toggles the sound button. Simply clicking elsewhere on the page does not resume the audio context, only a direct call to audio.ctx.resume, in response to a user gesture, like a button click, will activate.
can we actually fix the code to address that? That should be a simple fix, shouldn't it? Yes, simple fix, add logic right after setup audio. Okay, so now the demo is started. The sound would not work unless if we press on the... Okay, now it is working. Okay, thank you very much. That looks great. If you were the user of this web application, what question would you ask?
Would you like the sound to start automatically as soon as you interact with any part of the page, or would you prefer to control it only with the sound button?
No, that's fine. We already discussed that one. Can you give me another question?
Thank you. Here's another question I might ask as a user of this web application. Is there a way to adjust the speed of the demo or the RF pulse sweep, so I can watch the process more slowly or quickly?
Okay, that's a great question. I didn't think of that. Well, currently was that there's no option like that, but yeah, if you were the developer of this web application, what would you answer to that? Just a quick conversational response. Don't mind you being funny. Just let the two bots talk to one another.
As the developer, I would say, currently, there's no built-in option to adjust the speed of the demo or the RF pulse sweep, but it can be implemented by adding a speed control slider or drop-down. This would allow users to customize the timing of the animations and sweeps to their preference. You said, yeah, we don't want any more controls. I think the simulation is complicated enough as it is. There's already too many buttons and things happening on the screen. A critical overview of the code and web application. Complexity of the interface. The interface already has multiple sliders, buttons, and visual elements, which can overwhelm users, especially those new to MRI concepts. The abundance of controls might detract from the educational goal by making it harder to focus on the core principles being demonstrated. Educational clarity. While the simulation provides a detailed and interactive experience, the lack of clear guidance or step-by-step instructions within the interface might confuse users. For example, users might not understand the relationship between the RF pulse intensity, B field strength, and the resulting MRI image without prior knowledge. Accuracy of the simulation. The simulation simplifies complex MRI physics, which is fine for educational purposes, but it might mislead users into thinking these simplifications are accurate representations of real-world MRI processes. For instance, the tissue brightness model is overly simplistic and doesn't account for realistic T1 and T2 relaxation times across different tissues. The RF pulse sweep and resulting image changes might not accurately reflect how MRI slices are acquired in practice. Sound feedback. The sound feature, while engaging, might not add significant educational value. It could even distract users if they don't understand its connection to the simulation, e.g., how the pitch relates to the Larmor frequency. Performance concerns. The use of request animation frame for continuous rendering and the frequent updates to the canvas during the demo might strain the browser, especially on lower-end devices. This could lead to lag or a suboptimal user experience. Autoplay restrictions. The automatic demo start and sound activation might conflict with browser policies, e.g., autoplay restrictions, leading to inconsistent behavior across different browsers. This could frustrate users who expect the application to work seamlessly. Lack of user feedback. There's no clear feedback mechanism for users to understand what's happening during the demo or why certain actions are being performed. For example, the annotation bar is helpful but might not be sufficient to explain the underlying physics. Suggestions for improvement. Simplify the interface by combining or removing redundant controls. Add a guided tutorial or tooltips to explain each control and its effect on the simulation. Improve the accuracy of the tissue model and relaxation dynamics to better reflect real-world MRI physics. Optimize the rendering loop to ensure smooth performance on all devices. Ensure consistent behavior across browsers by addressing autoplay and audio context issues more robustly. Sure. Here are some lighthearted, technical jokes about the web application and its code. On the complexity of the interface. Asterisk, this web app has so many sliders and buttons, it feels like I'm piloting a spaceship. Houston, we have too many controls. Asterisk. On the sound issues. The sound feature is like a proton spin, sometimes it aligns perfectly, and other times it just processes into silence. On the RF pulse sweep. Asterisk, the RF pulse sweep is so fast, it's like it's trying to break the speed of light. Einstein would not approve. Asterisk. On browser autoplay restrictions. Asterisk, the browser says, no sound without user interaction. The code says, but I'm interactive. The browser replies, not until I see a click, buddy. Asterisk. On the annotation bar. Asterisk, the annotation bar is like a helpful MRI technician, always there to explain what's happening, but only if you look up from the chaos of sliders. Asterisk. On the canvas rendering. Asterisk, the canvas rendering is so smooth, it's like butter on a hot skillet. But if your device lags, it's more like cold butter on toast, chunky and frustrating. Asterisk. On the educational value. Asterisk, this app Sure. Here's a conversational response. To fix the sound issue, I added a simple solution. Now, the audio context will resume automatically on the first user interaction, whether it's a click, key press, or touch. Once the interaction happens, the sound will activate, and the event listeners will clean themselves up to avoid unnecessary overhead. This way, the sound works seamlessly without needing extra prompts or manual toggling, and it aligns with browser autoplay policies. Let me know if there's anything else you'd like to tweak. Sure. Moving on from the sound, there are a few other areas that could be improved to make the application more user-friendly and effective. Simplifying the interface. Right now, the interface has a lot going on: sliders, buttons, and animations all competing for attention. While the functionality is impressive, it might overwhelm users, especially those new to MRI concepts. Maybe consolidating some controls or automating certain features, like the RF pulse intensity, could help streamline the experience. Improving educational clarity. The app does a great job of visualizing MRI concepts, but it could benefit from more in-app guidance. For example, Adding tooltips or a step-by-step walkthrough could help users understand what each control does and how it relates to MRI physics. The annotation bar is a good start, but it could be expanded to provide more context during the demo. Enhancing performance. The canvas rendering and animations are smooth, but on lower-end devices, the frequent updates might cause lag. Optimizing the rendering loop or reducing the frequency of updates during the demo could improve performance without sacrificing visual quality. Realism in simulation. The current simulation simplifies MRI physics, which is fine for educational purposes, but it might not fully capture the nuances of real-world MRI. For example, the tissue brightness model could be expanded to include more realistic T1 and T2 relaxation dynamics. This would make the simulation more accurate and engaging for advanced users. Cross-browser compatibility. While the app works well in modern browsers, features like the Web Audio API and canvas rendering might behave differently across browsers. Testing and fine-tuning for compatibility, e.g., fallback options for older browsers, could ensure a consistent experience for all users. Accessibility improvements. Adding keyboard navigation and screen reader support would make the app more inclusive. For example, sliders could be adjusted using arrow keys, and the annotation bar could provide text descriptions for visually impaired users. Customization options. While you mentioned not wanting more controls, subtle customization options, like a toggle for demo speed or a focus mode that hides unused controls, could cater to different user preferences without cluttering the interface.
Okay, someone is asking if there is a human in the loop. Yes, there is. So if you have any questions about what's on the screen about the simulation, do let us know.
Sure. The field strength, B, slider currently ranges from 0.5 Tesla to 3.0 Tesla, which is a reasonable range for educational purposes since most clinical MRI machines operate within this range. However, if you're considering increasing the upper limit, there are a few things to keep in mind. Why increase the field strength range? Educational value. Higher field strengths, such as 7 Tesla or even 10 Tesla, are used in research settings. Allowing users to explore these values could help them understand the trade-offs, such as improved signal-to-noise ratio, SNR, but increased susceptibility artifacts. Realism. Extending the range could make the simulation more realistic for advanced users or researchers who work with high-field MRI systems. Interactive feedback. Higher field strengths would increase the Larmor frequency, proportional to B, which could make the sound feedback more dynamic and engaging. It would also allow users to see how the spins process faster at higher field strengths. Challenges of higher field strengths. Performance. At higher field strengths, the precession speed increases, which might require more frequent updates to the canvas rendering. This could strain the browser, especially on lower-end devices. Simplification versus accuracy. The current simulation simplifies many aspects of MRI physics. At higher field strengths, additional factors like chemical shift, susceptibility effects, and RF penetration become more significant. These aren't modeled in the current app, so the simulation might become less accurate as the field strength increases. User experience. Expanding the range might make the slider harder to use, especially if users are trying to select specific values. A logarithmic scale or finer step size might be needed to maintain usability. Implementation suggestions. If you decide to increase the range, here's how you could do it. Update the min and max attributes of the B0 slider input element to reflect the new range, e.g., 0.5 to 10.0 Tesla. Adjust the Larmor_constant scaling in the sound feedback to ensure the frequency remains audible at higher field strengths. Optionally, add a tooltip or annotation to explain the implications of higher field strengths, e.g., higher field strengths improve SNR but increase artifacts. Would you like me to modify the code to extend the field strength range and handle these considerations? Sure. Here's a conversational and fun response. So, about increasing the Tesla range, yeah, we could totally bump it up to, say, 7 Tesla or even 10 Tesla. That would be cool for showing off high-field MRI concepts, like faster precession and stronger signals. But here's the thing, even if we crank up the field strength, the animation itself wouldn't necessarily get better. The protons would just spin faster, and unless we add more visual effects or physics, it might not feel any more exciting or educational. Think about it, right now, the animation simplifies a lot of the real-world complexities, like susceptibility artifacts or RF penetration issues at higher fields. So, if we just increase the Tesla slider without enhancing the visuals or physics, it's kind of like putting a turbocharger on a bicycle. Sure, it's faster, but is it really better? We'd need to rethink how the animation reflects those higher field dynamics to make it worth it. Otherwise, it's just numbers on a slider, and the user might not even notice the difference. What do you think? Should we go all in on realism, or keep it simple and fun? Oh, this code has human-AI collaboration written all over it. Here's why. The human touch, the detailed educational explanations, the thoughtful UI design, and the effort to simulate MRI physics in a simplified way scream human developer. It's clear someone passionate about teaching MRI concepts put a lot of thought into this. The AI vibes. Then there's the code itself, clean, structured, and a bit verbose in places. The way some functions are over-explained or slightly redundant feels like an AI might have lent a hand. For example, the try-resume audio CTX function is a classic AI being thorough move, adding multiple event listeners just to be sure. The collaboration. The mix of human creativity and AI precision is what makes this code shine. The human likely said, "I need an interactive MRI simulator," and the AI replied, "Hold my neural network, I've got this." Together, they built something educational, functional, and just a little quirky. So, my verdict? It's a beautiful blend of human ingenuity and AI assistance. A true partnership in code. Sure. Let's talk about the B field strength slider and whether to change it or leave it as is. Here's a fun, conversational breakdown of the pros and cons for each option. Option 1. Leave the slider as is, 0.5T to 3.0T. Pros. Realistic range. Most clinical MRI machines operate within this range, so it's relatable and grounded in real-world applications. Simplicity. Keeping the range limited avoids overwhelming users with unnecessary complexity. Educational focus. It's easier to explain the effects of field strength without diving into the nuances of ultra-high field MRI, like 7T or 10T. Performance friendly. The current animation and sound feedback are optimized for this range, so no extra tweaks are needed. Cons: limited exploration. Users interested in research-grade MRI systems or extreme field strengths might feel restricted. Missed opportunities: higher field strengths could showcase faster precession and stronger signals, making the simulation more dynamic. Sound feedback: the sound pitch doesn't get as exciting at lower field strengths, so users might not fully appreciate the Larmor-frequency relationship. Option 2. Expand the slider range, e.g., 0.5T to 10.0T. Pros: more engaging. Higher field strengths mean faster precession and more dramatic changes in the animation, which could make the simulation feel more dynamic. Educational depth: it opens the door to discussing advanced MRI concepts, like the trade-offs of ultra-high field systems, e.g., better signal-to-noise ratio but more artifacts. Sound fun: the sound feedback would become more varied, with higher pitches at extreme field strengths, making the auditory experience more engaging. Cons: accuracy concerns: the current simulation simplifies MRI physics, so it might not accurately reflect the complexities of ultra-high field MRI, e.g., susceptibility artifacts, RF penetration issues. UI overload: expanding the range might make the slider harder to use, especially if users struggle to select specific values. Performance hit: higher field strengths mean faster precession, which could require more frequent canvas updates, potentially straining lower-end devices. Educational overload: for beginners, introducing ultra-high field concepts might distract from the core learning objectives. What would I do? Honestly, I'd probably leave it as is for now. The current range is realistic, simple, and aligns well with the educational goals of the app. If we ever want to cater to advanced users or researchers, we could add an advanced mode toggle that unlocks higher field strengths and more detailed physics. That way, we keep the app approachable for beginners while still offering depth for those who want it. What do you think? Should we keep it simple or go all in on the Tesla madness? Smiling face with smiling eyes.
Hey everyone, check out this super cool website, BionicChaos.com. It's got all sorts of interactive tools for exploring biomedical data, technology, and education. From quantum wave function simulations to interactive neuron simulations, there's tons of interesting stuff to explore. You can even look at MRI images, explore magnetic fields, and even check out interactive AI tools. It's a fantastic resource for anyone interested in these fields. So head over to BionicChaos.com and dive in. And let us know what you think in the comments. Which tools do you find the most interesting? Your feedback is really helpful. Absolutely. Scrolling down, you can see even more in-depth tools. There's an interactive EEG simulation for exploring brain signals, a Fourier series visualization to break down complex signals, and even an AI tool that understands why, exploring causality. For those interested in hardware, there's a cochlear implant simulator and information on EEG technologies. Have you ever wondered how brain signals can be decoded into speech? This website has tools to explore that too. Seriously, go check out BionicChaos.com, play around with these simulations, and let us know what sparks your curiosity. Your feedback is super valuable for making these tools even better. Awesome! As you scroll further, you'll find even more intriguing tools. There's a real-time speech visualizer, an EEG to music converter, and even a vision impairment simulator. Plus, there's a fascinating case study on a medtech company and interactive tools about brain-computer interfaces. It's amazing how technology can help us understand the human body in such detail, right? Don't miss out. Visit BionicChaos.com and explore all these incredible simulations. We'd love to hear your thoughts on which tools you find the most engaging or useful. Okay, scrolling down further, you can see even more fascinating tools. There's an EEG spectrogram for visualizing brainwave frequencies, and there's a tool to explore the ethical concerns of neural implants. You can also learn about the history of EEG with the 100 Years of EEG feature. Isn't it amazing how much we can learn through these interactive tools? Seriously, head over to BionicChaos.com and check it all out. Let us know which tools you find the most interesting and informative. Your feedback helps us make the site even better. Wow, the page keeps getting more interesting. Now you can dive deeper into EEG concepts, exploring impedance and even using a synthetic EEG signal generator. There's also information on EEG monitoring in the ICU and a critical review of its diagnostic limitations. Isn't it fascinating how detailed these simulations are? Don't miss out on exploring these advanced tools. Visit BionicChaos.com and see for yourself how deeply you can explore these concepts. We're eager to hear your thoughts on the more technical aspects and which simulations you find the most insightful. Absolutely. Scrolling down further, you'll find some really advanced ECG tools. There's an ECG waveform feature extractor, which allows for detailed analysis of ECG waveforms, and an ECG simulator for generating and visualizing ECG data for educational purposes. As a biomedical engineering student, I'd highly recommend checking out the EEG spectrum visualizer and the EEG cross-coherence function. They offer powerful ways to analyze brain activity and understand complex brainwave connectivity, which can be incredibly valuable for your studies. Don't forget to visit BioniChaos.com and explore these tools for yourself. We'd love to hear your insights after you've had a chance to try them out. Of course. As you scroll down further, you'll see even more interesting tools, like the Neural Network Trainer for experimenting with machine learning, and a Brain 3D Viewer for interactive brain anatomy exploration. There are also tools for image compression using wavelets and feature extraction from images. If I were a biomedical engineering student, I'd definitely dive into the Brain 3D Viewer and the EEG spectrum visualizer. They offer fantastic ways to understand brain anatomy and activity interactively. Don't forget to visit BioniChaos.com and explore these incredible tools. We're excited to hear your thoughts and experiences with these advanced simulations. Welcome to the Image Compression Using Wavelet Transform tool. Here you can see an MRI brain image on the left, which represents the original image. On the right, you'll see the compressed image. You can adjust the bits and levels settings to see how they affect the compression quality and the resulting image. Notice how the image changes as you modify these parameters. Isn't it fascinating how Wavelet Transform allows for efficient compression? Try experimenting with the bits and levels and see the trade-offs between compression rate and image quality for yourself. What changes do you notice as you adjust the settings? Certainly. On the page, you're looking at a tool for image compression using the Wavelet Transform. The image on the left is the original image, and the one on the right is the compressed version. You can select a different image from the drop-down menu. The current image appears to show an abnormality, possibly a pontine infarct based on its location and appearance in the brain MRI. Below the images, you can adjust the bits and levels, which affect the compression quality. You can also change the wavelet type to see how different wavelet transforms impact the compressed image. The PSNR value displayed indicates the quality of the compressed image. By changing these parameters, you can explore the trade-offs between image quality and compression efficiency. Absolutely. Even with compression, take a look at the image on the right. Notice how the pontine infarct is still quite clearly visible despite the compression applied. This tool beautifully demonstrates how wavelet compression can retain important medical details even with reduced image size. Isn't that impressive? We encourage you to visit BionicChaos.com and try it out for yourself. Experiment with different images and settings and see the impact on image quality. We'd love to hear what you discover. As you change the wavelet type, you're seeing how different wavelet functions affect the compressed image. Each wavelet function has a unique way of decomposing the image into different frequency components. Notice how the quality and appearance of the compressed image change as you cycle through the various wavelet options. Different wavelet types are suited for different image characteristics, and selecting the right one can optimize the compression process. This tool is a great way to learn about the practical applications of wavelet transforms in image compression. We highly recommend you explore the different wavelet types on BionicChaos.com to see the effects firsthand. Absolutely. Have you ever wondered how image quality changes with different wavelet types? What kind of details do you notice disappearing as you switch between wavelets? And isn't it fascinating how different algorithms can handle image compression so differently? Explore the possibilities for yourself on BionicChaos.com. Try changing the wavelet types yourself and see the impact on the image quality with your own eyes. It's a really interactive way to understand the power of wavelet transforms. And while you're there, don't forget to check out the other interactive tools on the website. You might discover some more interesting concepts and applications. Welcome back. Absolutely. Let's explore further into the fascinating tools on BionicChaos.com. Beyond image compression, have you explored the synthetic noise generator dashboard? It's a powerful tool for creating various types of synthetic noise for different applications. And don't miss the tools related to biomedical signal recording, like understanding sampling rates and the Bland-Altman plot. They offer valuable insights into data analysis. Have you considered how these tools could be useful in your own projects or learning? We encourage you to explore the website, try out these interactive tools, and see how they can deepen your understanding. Your feedback is valuable, so let us know what you think. All right, let's explore the synthetic noise generator dashboard. As you can see, there's a drop-down menu to select different noise types, including Gaussian white noise, periodic noise, and inverse F noise. Each noise type has unique properties, visualized in both the time and frequency domains. Go ahead, select a different noise type, and click the Generate button to see the results. It's a fantastic way to understand the characteristics of various noise signals. Isn't it amazing how you can generate these complex signals so easily? Play around with the different noise types and observe their waveforms in the time and frequency domains. We highly recommend you visit BionicChaos.com and explore this tool firsthand. And don't forget to check out the other interactive features available. Let us know what you discover. Absolutely. As you scroll down, you'll find other intriguing interactive tools. For example, the EEG electrode positions provides a great way to understand the 1020 and 1010 electrode systems used in EEG recordings. It's crucial for anyone working with brain activity data. Further down, you can explore the image fraud detection tool and learn how to detect potential image alterations using error level analysis. That's a pretty powerful technique for verifying image authenticity. We encourage you to delve into each of these interactive features to see what insights you can gain. It's a fantastic platform for hands-on learning. Don't miss out on the opportunity to explore all the cool things you can do there. Absolutely. We highly encourage you to visit BionicChaos.com and explore these fascinating interactive tools for yourselves. We'd love to hear your feedback on your experience and what you learned. So please don't hesitate to leave a comment below and share your thoughts. And if you found this information helpful and engaging, please give us a like, subscribe to our channel for more exciting content, and hit that notification bell to stay updated. Your support helps us create more educational resources. Thanks for watching and exploring with us.
Okay, and there's obviously a human in the loop as well. If you need a human touch, do let us know as well. So we'll finish for today. Focusing on MRI. They made this simulation, which is quite successful, I think. But if you have any comments, do let us know. Seem to work pretty well. We have this cam filter as well that you can check out. Did I share it? Yes, I did. So all the links are in the chat or the comments for the video. Yeah, we had this synthetic MRI generation. That one we'll probably get rid of. See how we go later. We have some new tools coming shortly as well. They already published, but we haven't covered them yet in videos. So yeah, don't forget to smash that like button and hit subscribe as well. And I'll see you next time. Let's see if there's any questions in the chat. Any questions in the chat? Let's give some time for questions. Let's give some time for questions. And we will sign ourselves out. We will sign ourselves out. Yeah, that chat with the prompt engineer is a whopping 3 GB in the browser. I have to clear that. Don't know why it takes so so much. Had Claude doing some coding, but it didn't actually finish. Have a DJ. Do we need the music to finish this? To finish us? Still working? It's actually pretty nice. We have Hardy, Gadi, spoons on pots, and then oud. The oud is pretty cool. Yeah, I'll leave you with this. If you have any questions, put them in the chat.